start. One day it will actually generate a good theorem, and then it's stuck with someone.
I think we should start. Are you ready?
Yep.
Excellent. So welcome everybody to this first session on the last day. Glad to see so many in the early hours. And it's the last session of Bob talking about polynomial time and type theory. So go ahead.
It's polynomial time.
Hey.
Go, Bob.
Less complexity. Faster.
Yeah, we all feel a bit like that.
Okay.
Smooshed around the edge.
Go on it. Okay, so how can I hide? Okay, so far we've seen, let's do a recap. So on Tuesday, I introduced the linear lambda calculus. And then on Tuesday and Wednesday, showed how by adding special data types of a certain form, you could capture, well, at least I claim, you could capture a polynomial time using the language. So every program that you could write that was sort of a natural number to something ran in polynomial time in the size of that natural number. So by adding special data types, E time, and then yesterday we went through, sketched the realizability model used to prove P time soundness. And I kind of hope that even if you're not interested in complexity analysis, just sort of seeing, if you haven't seen it before, realizability models is interesting. And they're a great way of proving things about typed lambda calculi that you may invent. And you may wonder, I think it has this property, can I prove it? And using realizability, especially realizability with some kind of notion of resource, can work really well. So today, we're going to get on to the type theory proper part, which I thought we'll get to earlier. So we're running out of time, and want to combine linear and dependent types so that we have a unified calculus where we can not only use the linearity to get restricted complexity programs, but also use dependent types to reason about those programs. And this is useful because there are complexity classes which are characterized not only by the fact that they run in a certain time, but they compute the answer in a certain way. So for instance, non-deterministic polynomial, we have some problem we're trying to solve. The program is allowed to make, or allowed to assume that there's some supply of bits which guide it in this, but we have to know that what the problem that we're trying to solve is, so we can say that there's actually this program solves this problem in non-deterministic polynomial time. Similarly for the probabilistic classes, I'll get to it again. So we want to say that this probabilistic program, which is allowed to do coin flips as it's going, must say the right answer 2/3 of the time, also 2/3 probability. So this is why we want to combine linear and dependent types so that we can have a dependent type theory that has as a subsystem one of these linear type systems for polynomial time. Okay. However, combining linear and dependent types is sort of falls apart as soon as you try and think about it. So the main problem is that there's a sort of fundamental clash about how they use variables. So here's a simple dependently typed program. written out as a typing derivation, or typing judgment, sorry. Okay, so it's super simple. There is a nat in the context, and then there's a finite, so this is fin, so it's the type of natural numbers less than this number. And all it does is return this number, which is less than x, as the program, right? So if we want to treat this as a linearly typed program, where we're kind of stuck if we're just thinking about linear means variables only appear once. So we've got y certainly only appears once, and in some sense this is linear, in the sense that it uses input once. But this x, for one, doesn't appear in the term, so we don't use it, but it appears twice in the types, so we do use it twice. So is x linear? Can we treat this thing as linear? And at some kind of high level, the problem is that in type theory, variables have a kind of mixed logical and computational meaning. They're there in order to form the types. So this x is just used to form types. We don't really need it if we were to imagine that we run this program. So variables have mixed computational and logical meanings or uses. But in linear logic, every variable is there because it's used by the program, or in affine sense, is may not be used, but it's going to be used at most once. So the presence of a variable tells us that we're using its resources. The presence of a variable or not is important. But for type theory, we can just weaken this by adding more variables, and it doesn't, it just weakens the logical statement of the judgment, but it doesn't affect the derivability. So how can we fix this? So an old solution, which I think the original presentation is due to Servosato and Fenning in the linear logical framework, is, well, let's separate the logical uses, the kind of what I call the intuitionistic context, from the linear context. So they would, as a matter of notation, write this program like this. They would have a bar that would clearly separate these two contexts. Okay. So now to the left, this is sort of the context of things which can be used intuitionistically, as in normal type theory. And over here, everything works as it does in normal type theory. Then in here, we have a linear context of linear assumptions. And the types of these are allowed to depend on things in here, but not on earlier things in the same context. So this is entirely non-dependent. And then over here is a linear type as well. So we really split the world into two judgments. One is the traditional type theory judgment, like this. So M has type A in context gamma. So this is usually called intuitionistic or unrestricted. So that's obviously relative to the linear restriction. And then the other judgment is like this, where we have a linear term type X in so this is double context. So again, this is the same kind of context as here. These are intuitionistic variables. The formation rules for these are derived from this judgment. These are the linear assumptions.
Like, is there any restrictions on the M? Like,
This M?
yeah.
No, so this, well, it depends exactly on the system. So I'm talking about a big family of systems. Typically, these will be at least the same as you get in normal type theory, like that on contrary.
Okay, so like I'm talking about, you are defining a new language, right? So any term from that language can be in, like, so you're dividing it into two words.
Yeah.
That's what you're saying. So I'm saying that, so in one way there is a typing judgment that derives in the, like, how we derive things normally.
Yeah.
So I'm asking, like, are you saying that in that sense, I mean, that judgment only target a subset of the language or the entire language?
Yes, yes. Oh, yeah, so, okay, so, yes, these are two different syntactic categories. So these are, these terms will look like the standard ones of type theory, so lambdas and sigmas and so on, pairing. These ones will look like the linear lambda calculus terms from earlier. So they'll have, in particular, lets for taking apart tensor products. The story gets a little bit more complicated because, of course, you don't want these two things to be completely separate. So often there will be some kind of modality that takes us from the linear to here. So it's like a bang, essentially. And there'll be some other modality which takes us from here to unwrap the bang. But I don't want to spend too long explaining it. The point is that we do separate the worlds into two linear, so non-linear and linear worlds. And linear can depend on non-linear, but not the other way around. There are quite a lot of variations on this general setup. So depending on whether or not the syntactic categories of types are actually the same or different, or you have completely separate types. And this sort of, one might say, it spoils the nice world of dependent types where anything can depend on anything else. However, it does make it super clear what's going on. And if the linear world is radically different from the intuitionistic world, then this is sometimes what you want. So here you might say, for quantum programming purposes, this is the classical physics world. We're allowed to do what we want. And down here, this is qubit, 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 and this is qubit, 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 qubit. And then this L is describing a circuit of some sort. And we keep the two very separate. Okay, but for the purposes of programming with polynomial time, we would like to depend on linear terms because we want to depend on, if we have a linear function that goes from nat to bool, for instance, and we know it's polynomial time, then we want to take that linear function and then speak about it and reason about it. So we want to depend on that linear function itself. And here, we can't depend directly on linear terms. There's this gamma only allows us to depend on intuitionistic things. So what we're going to do is take this idea I mentioned on Tuesday of systems where instead of using the presence or not of a variable in the context to talk about linearity, they mark the variables with how they're used with elements from some semi-ring. So we're going to have, so if you recall, we have judgments that look like this. And these, each of the colons in the type assignments are annotated with a row, which comes from some semi-ring. So just for now, think natural numbers. How many times is this variable used? So again, we capture some kind of linearity. And the key insight, which is, thanks to Connor, is that we're allowed to say we're not using something, which is 0. So we might as well say, okay, but it still exists in some sense at some sort of compile time or some contemplative level. So we can use that to appear in the types. So 0 annotated things, or let's say the other way around, things which appear in the types are classed as being used 0 times. And the nice thing here is that because adding something to 0 just gives you the something, this doesn't affect the accounting for how they're used in the rest of the term. So to make this work for dependent types, what we're again really going to do is split the world into linear and nonlinear worlds, but in a way that allows a bit more merging or conflation, if you like, of the term languages. So really, we're going to split into two judgments. So this judgment at the top works well for simple typing. But now we're going to split into worlds where we have the gamma and m, and now we're going to annotate the result one. So 0 is going to be the terms which live linearity free. So this is the academic world where we're free to do what we want, resources don't matter. We haven't got any. So, you know, you can double your money back where you started. And this is what the Daily Mail thinks of academics. We can just do what we want, doesn't matter, and so on. Over here in the real world, where people do useful things, things matter. There's a 1. This is the real world, so linearity restrictions now apply. So in particular, it will be it's a kind of admissible rule of the system that, in fact, when we generate something that's used that has 0 annotation here, everything in here will be 0 annotated. So it takes nothing to make nothing. Whereas over here, this gamma might have quite a rich amount of usage annotations applied to each of the elements. I should say one wrinkle with this system is that in the simply typed world, there's quite a rich array of semi-rings you can use. Things like sort of security lattices, where you think about the order as like information may flow from here to here, or monotonicity, or things like that. In this world, we're a bit more restricted in that the semi-ring we're allowed to use must be one that's essentially counting-like. So it actually has these properties where we must have that if x, if rho plus pi is equal to 0, then rho equals 0 and pi equals 0. And if rho dot pi is equal to 0, so we must have these properties in our semi-ring, which actually is similar to Jamie's properties for encoding logic. And so these essentially mean that the numbers are going to be counting something. They act like counting numbers. And the key admissible rule of the system is this zeroing rule, which says that if we have something that lives in the real world, then it also lives in the resource-free world. And this is sort of the extensional counterpart of the linear term. So every linear term, this M, is going to have the sort of part of the trick that makes this system work is it's exactly the same syntax. This is really a trick. It has an extensional content that we can depend on in the types. So this is a way of answering what does it mean for a type to depend on something which has resources and has is a process and things like that. And so here we're just saying by fiat that every linear term has some kind of normal type theory counterpart. Yes, Katie.
Just checking. You described when you wrote that down, you described it as a key admissible rule.
Yes.
And I was slightly upset because you didn't have 2 horizontal lines instead of 1.
I've used 2 horizontal lines for an invertible rule.
Oh, okay, fair enough. Thank you. But then you said we've decided by fiat.
Oh, well, no, okay. This if you ever break this, then it's by adding extra rules, then something's gone wrong. So
Okay, so it is an admissible rule, but it's in the design of the system
Yes.
that it should be.
yes.
Thank you very much.
Okay, so this is called zeroing. Okay, and just in case anyone has not heard the word admissible before for these rules, admissible means that this is a rule which is derived, like, given a judgment of this form, you can derive one of this by rewriting the derivation of this. It's not actually a rule of the system, in the same way that substitution is admissible, but it's not actually a rule of most systems. Okay, and so this system is called quantitative type. Okay, so quantitative type theory because it counts the number of times each variable is used, and we're going to use that for the linearity. Also, quantitative has too many T's in it. I always spell it wrong. Okay, so doing good for time. So I'm not going to give you all the rules of quantitative type theory. I'm just going to well, I don't think you'll be able to reconstruct them from this quick description, but the point is that there are really two worlds, but we can give most of the rules by just abstracting over whether we're 0 or 1. And that allows us to have quite a compact representation of the system. So I'll just write sigma for when it's 0 and 1. But the key thing to remember is that in the 0 world, we're relatively unrestricted. In the 1 world, we have to account for all the resources we use from the context. Okay. So how do we apply this to the linear polynomial time type systems from before? So I'm not going to go through why the functions and the product types work, but I'm going to cover how we integrate the data types from the cons3 and the LFPL systems we saw in the last few days into this system, and where we have to put the 0s and 1s and so on into the rules. So let's do QTT plus cons3. So remember, this is the system where we have a natural number data type that we're allowed to iterate over, but not construct. So this natural number comes from the input. It's always a fixed size. We can iterate over it. We can duplicate it and iterate over it in nested ways so we can get polynomial time. But we can't ever construct new things to iterate over, because as we saw, that allows us to bootstrap our way up this hyperoperator hierarchy where we get multiplication and exponentiation and so on, and just defeat any kind of polynomial time guarantee. However, in this world, we do want to be able to construct natural numbers because we want to be able to use them to reason about programs which may be of restricted complexity. So in the 0 fragment, we can construct natural numbers completely freely. So we're going to have these rules. So this is a 0. And we can construct in the 0 fragment, so there's another 0 there, one of these heavy natural numbers. And just in the style of how I'm writing these things, this judgment at the top means that's a well-formed context. This is just because now contexts themselves are quite complicated things. And again, in the 0 fragment, if we can construct a number n, which is a heavy one, you can construct its successor.
So on the left side, is it just an arbitrary context, or there's like some multiplication on 0 going on?
So I use this. It basically means that everything in the context has 0 usage. Okay. And this is just a shorthand way of saying that, because whatever gamma was, it gets zeroed out. Okay. So I could say it's gamma and everything in gamma has 0 usage. Okay. In other words, this is just a shorthand way of saying it. Okay. So we're only allowed to construct these in the 0 fragment. And that zeroing rule went from 1 to 0, but not the other way around. So we can't get these in the 1 fragment. We still cannot construct in the 1 fragment where you have a 1 on the colon. We can't construct any natural numbers. But we can iterate on them. And so now I'm going to give you this sort of typing judgment for the iterator. So now we have 2 things to add to what we had before. One is it's dependently typed. So we're going to have the result type is going to depend on the input. So this gives us an induction rule. And we're going to have to correctly annotate things with what is and isn't available to the linear term by putting the zeros in the right places. So the first thing we need to do is to establish our inductive hypothesis. So this is itself is just a type. So I'm using this judgment P as a type to say P is a proper type. In this context, in particular, it has a free variable X of type map. And this is annotated with 0 because we're just using it to construct a type. Yep.
Which now?
Oh yes, the heavy. Yep. So the question was which nat, and it's the one with the filled dot. Then we give the 0 and successor cases. It's in the same context. So we have to give a term mz, which doesn't use any resources, but we might have to have some things in gamma in order to construct this p type, right? Because the p depends on things in gamma. And we substitute in for x 0, because we're doing the 0 case. So this is, we have to prove, basically, we have to prove our property p when x is 0. And we're allowed to do this here because this is all in the 0 fragment because it's in the types. So we can use this typing rule up here to construct the number. Now in the step case, yep.
And just ask, why in the 0 case do we need 0 resources on gamma? Because we're only going to use it once, right?
So the question is, why in the 0 case do we need 0 resources on gamma? Because there's only 1 0 in every number. Yeah. We could, it's just for uniformity reasons, it makes it easier. Because when you have, yes, you could. But, right, okay, so a slightly less flippant answer is, if you ever find yourself needing something in here which is not zeroed, then you can make p into a function, and then you can pass it through the whole thing. So we've got functions in the language, so you just pass it through here, which makes some programs slightly mind-bending to write, because you have to abstract earlier than you think you should. Okay. Now in the step case, in the simply typed world,
Yeah, probably this is a question because I'm not having a proper understanding of the bigger context in which it is happening. So at the beginning, like you said that the reason why we have to like distinguish between the two worlds is that we can use a variable at the term level and also at type level. That means two different usage.
yes.
Right. So we already know that, right? I mean, so we already know that, like when we already know that distinction. So why have to do like, I mean, so I'm thinking the reason why we have to do that in the meta level by like, so you're distinguishing between two categories, right? I mean,
yeah.
in the formalism itself, like using the meta logic. So is it for a correctness from that, like from the construction of the things that you separate things instead of keeping the difference in our mind?
So we have a difference in our mind. I would claim that in the semantics, the difference gets erased.
Oh,
Okay. There's no clear way it's separated
all right.
without having to do something like this.
All right. Yeah.
I think, or the split context.
Okay. Yes.
setting,
Thanks.
yeah. Yeah, so all right, so in the simply typed setting for the step case, we had access to the result of processing the predecessor natural number. But here we're going to have to form the final result, which is going to be P of successor of something. We have to have that something to talk about. But we can't give the programmer access to use that at runtime, but it has to exist here for typing purposes. So we're going to have n, which is 0 usage here. And the recursive data from P is n for x. And we have to write a term ms. Like this, right? So this is an n. So we have the n, but we're not allowed to use it linearly. Right? We're not allowed to, we can use it to form types. We can go in here and here, but we can't use this n in ms in a way which is relevant to the computation. But we can use the r, so we're going to annotate that with 1. So this is the step case.
What about an annotation for MZ?
Oh yeah, I'm going to come back to it. Yes, yeah. Yes, good. I haven't annotated these yet, but we're going to. Yeah, so this is what we can do now is we can say this is used at compile time. This is going to be used at runtime, and we're going to generate something which is used at runtime. So if QCT does nothing else, it allows us to talk about what's erased at compile raised before we get to runtime. And this is sort of essential to actually using dependent types as a programming language, because otherwise we end up keeping huge amounts of information around that we don't actually need. And finally, we need to actually have a natural number to iterate on, and that comes from some resource gamma. And as Jesse pointed out, there's no annotations on these colons. And there's 2 rules going on here. One is the iterator in the 0 fragment and this iterator in the 1 fragment. So I'm just going to do both of them at the same time by saying this is just sigma everywhere. And then we just put all the bits in here, and then the final result is in sigma. And we get a result which is p with n replacing x.
This is an important lesson. Now that Bob is using a variable to stand the thing that is in common across all the important judgments. But Bob is actually using a sigma. What I would do in this situation is use the absence of the annotation to mean uniformity across 0 and 1, when Bob is actually drawing attention to the fact that there's an abstraction going on. And I would get my thing rejected.
Paul, I have a few naive questions which, with your permission, I'll ask, and you have my permission to ignore them. One is, at the start of this lecture, you talked about a system with split sequence. There was a linear half and a non-linear half.
Yeah.
And it seems, if one were inclined to reject this paper, one might say, well, this is just a representation of that, because we see the 0 stuff is the non-linear half and the 1 stuff is the linear half. So what more is going on here than reformulating the spirit of the system you mentioned at the start? That's one question. Another question is, it's quite remarkable that everything that happens in the 1 world, that there's not more happening in the 0 world here than there is in the 1 world. It's still the same rule, still the same iteration.
Yeah.
What should that tell us? What should we learn from this fact? Would it be possible to have another type system with a more powerful rule in the 0 case and the 1 case? That's the second question. And the third question is it's really interesting that you've mentioned compile time versus runtime, and there's these systems with split sequences. What's going on here? Is this canonical? And I'll stop there. Thank you.
Yeah. Okay. So first question was, is this really just is there any kind of big difference between this and the split context system? And no, well, it's a little bit complicated. So what's really going on here is that if you imagine a canonical use of the split context system, where the two contexts are always extended in lockstep. So we have, for every entry, we have an intuitionistic part and a linear part. And they're always combined in lockstep. And that's really what's going on. Excuse me. What's going on here is like every time this context gets extended, it's going to have, every type has an intuitionistic part and a linear part. And it's the zeroing which just erases the linear part or forgets it. So all of the models I have of this system start off essentially being split context things. They are some model of normal type theory that index a symmetric nodal category. But it's just used in a certain way where every type combines the intuitionistic part and the linear part. So it's, in some sense, it's a particular mode of use of these of the split context system that happens to work well. It does have other slightly more subtle changes. One is that types are differentiated by, even if they have the same values in the zero fragment, if they've got different resource interpretations as linear types, they're not equal. So in the zero fragment, we have this heavy NAT type, and we have the other one where which I'm not going to give a typing rule for, but the NAT with the hollow, which is in the earlier lectures. And you can prove that they are isomorphic in the zero fragment, but they're not the same, they're not equal types on the nose, because every type contains the resource information. There's some, like, I'm not claiming this is the best system, and there's certainly some weirdnesses going on in the system. It's I feel like it really is a mode of use of the, what's really going on is there's still a complete distinction between the linear and the intuitionistic worlds. Here, there's almost a syntactic trick to conflate the two to make it work.
So you're being purposely vague on which summary you're using?
Yeah.
Right? Which one would you use?
Oh, for this, you
Yeah.
have to use natural numbers.
So you do use natural numbers.
Yeah,
But
so
that
if
means you
you-
don't have to do explicit copying, right?
Yeah, so if you have the omega, you're back in the world where you can do unrestricted duplication.
But if you were doing two contexts, you would have to explicitly duplicate things
Yes.
in the linear fragment, which is a pain in the.
Yes.
I have another question. So how does it work if the sigma is instantiated to 0 with the, because there's this R which has a 1.
Oh,
it's
right.
used
Yes, sorry. Yeah, you have to make that a zero.
Okay, thank you.
And which, if I was doing what Connor said, that would have happened automatically.
I also have a naive question. So here, if the n is big enough, the 0 is going to be used once, but the step case is going to be used many times.
Yes.
But the rules don't represent that. They both check that the sigma quantity, right?
Yes, this is just for uniformity's sake.
Right.
Just
So
to treat every constructor the same.
is there no way to say that the step case is going to be used many times by the
Oh, right.
iteration?
All right. So
It's a zero.
it says 0. So in principle, yes, you could have something here which says anything here which would allow duplication. However, the semi-ring here has to be the natural numbers, because otherwise, if you have an omega, then you're going to have complexity the same as at least the simply type lambda calculus. But in general, yes, you can make sure this was omega, and then you can duplicate this context over and over again. So anything which has a kind of fixed point that is x is equal to 1 plus x. Then it's going to work. Another question?
Yeah, I have it a little bit scrambled in my notes, but I just wanted to verify, does rho indicate how often something can be used or has to be used?
Has been used.
Has been.
Yeah, so it's this is another subtle point to think about these quantitative systems. If you think about, I think it's helpful to think in the way Connor was talking about the inputs and outputs of the judgments. So the way you check this is that the context would come in, but not have any quantities on it. Then you check the term, and if you're synthesizing, the type comes out, but also the quantities come out, because it's an analysis of how that term used those variables. So it's how they are used by the term, not how they can be used. Is there any more? Okay, so that was the cons free system. And yeah, so when sigma is 0, this essentially becomes the normal eliminator for natural numbers in a dependently typed system. So it's completely unrestricted. You can do induction on the natural numbers. For QTT plus LFPL, so remember LFPL, not LEPL. LFPL was the system where, rather than banning construction, we pay for construction as we go. We're using these diamond types. So we can see here, this is going to be an example where the 0 fragment has sort of dramatically more power than the 1 fragment. So we have a type formation rule. So I'm just going to say this. So for any well-formed context gamma, where we're not using any resources, then diamond is a type. And now, previously, we couldn't construct diamonds, right? We only get the diamonds from the input. But in the 0 fragment, we can construct diamonds because they don't mean anything. Like money means nothing to us. We're just pure researchers. So here, we just talk about money as if it was some abstract thing. Right, we're allowed to construct a diamond, and this will allow us to create natural numbers or any kind of other inductive data structure in the 0 fragment. And indeed, it acts as well like a unit type. So we have the eta rules. So if we have any other M of type diamond in the 0 fragment, then M is equal to the star. So not only can we construct diamonds, there's only one in the 0 fragment. So this kind of tells you that really this is a unit type, but it has some resource weight to it. So it's not literally equal to if we had a unit type written down. And then we can give the typing rules for 0 and successor. So now if we have a diamond in some sigma, and if we have a natural diamond, then we can construct I'll write that properly. So if we have a diamond D, we can construct a 0. If we have a predecessor and a diamond, then we can construct a successor. And this works in any of the 2 fragments. So now the sigma could be the 0, 1. So now we can construct in both fragments. But of course, when sigma is 0, we can use this rule up at the top to just get us diamonds for free to plug in to make the natural numbers. And then the iterator is basically the same. So I'm going to do something I have not rehearsed. And try to modify this in place, because we can do in place update with Diamond. I'm going to have to move these over a bit. So now we get a diamond in here, but we have to supply a diamond here, but we can just use star. We have a diamond in here, and we have an extra D here. Now we need a. So again, the special thing with LFPL is that the construct takes diamonds, and when we iterate, we get the diamonds back. And that means we can construct substructures to iterate over again to get polynomial time. Okay, so now in the last 10 minutes, I want to sort of talk very quickly about how to use these systems. So now we've combined linearity and dependent types. How can we use these systems to actually talk about complexity theory? And this is still quite early work. I'll give it a go. So the first thing we need to do is to have a way of getting from the one fragment into the zero fragment. So before there was this zeroing rule, which took something which was in the one fragment and then just forgot that it was realizable. So this is very much like if you think about the realizability semantics, we forget the realizability relation and the fact that terms are realizable. We just remember the set theoretic part. But we want a different one where if you imagine that, as I said, the realizability relation doesn't necessarily say that everything is realizable. We want a way of taking any type and restricting just the things which are realizable. So in particular, given a function type, we want to restrict to just the set theoretic elements that actually have a polynomial time realizer. So we're going to embed that in the system by having an extra reflection rule or reflection type former. And this has this introduction and elimination rules. So if we have a term in the one fragment, which is resource closed, right? So it's self-contained with respect to resources. So in most cases, this A will be a function that takes in the additional resources, but it has to be resource closed. So all the other variables it uses are just for forming types. Then we can restrict, we can say, well, this is actually a member of the realizable members of A. This is going to write this as RA. So this is given any type, which if you think back to the realizability semantics, a type consists of a pair of a set and a realizability relation. This RA restricts the set to those things which are realizable. Right, so before we could have things which weren't realizable. This accounts for the fact that we can write things in a zero fragment which don't have any linear correspondence. But now we're restricting that type to just the realizable things. This is the introduction rule, and then the elimination rule simply goes back the other way. And here, if we've got something which is realizable, and it doesn't matter what fragment it's in, because we're just restricted to realizable things. So we know that M is realizable, then we can, in any other fragment, so if sigma prime is 1, then it's okay, because we knew that this was a realizable value of type A, so we've got the realizer. If it was 0, then it's okay, because we had the extensional content all along, the set theoretic content all along. So this allows us, in particular, on the top left one, if A is mapped to some more complex type that describes a polynomial time computation, this gives us a way of taking back into the zero fragment, so the plain type theoretic world, the fact that this is realizable. And we can use this to define p time as a type within the system. So polynomial time is the problems which are solvable in polynomial time. So first we have to define what a problem is. So we're going to say a problem is a set A of instances of that problem. This is going to be the type of graphs that we have to find, pass through, or whatever. And the predicate such that really this should be prop, but I've already got set. So this is the instance of the problem, and then this tells us whether or not that's a good instance. These are all decision problems. This is like, is it the case that this is something in our thing? So this is the classical kind of decision problems from complexity theory. Yep.
So I'm still looking at the rules.
Yeah.
Can I think about R as some kind of a fixed style modality on the usages? It's kind of locking everything.
It might be, yeah, there might be a nicer way of saying it, yeah. I don't know. It's, yeah. Right, so these are problems, and we can define p time. The problem is in p time if we have an f, which is a realizable all right, this is a lollipop linear function. Okay. This double arrow just means that these are equi-inhabited. So if there's an inhabitant of this, then there's a proof that this equals true. And if this is equal true, then there's an inhabitant of this. Yep.
Should A be a type rather than a set? Because then you're constructing the function space like linear, or is it linear functions in set?
I just mean set is the universe type in this system. I can't write type. Type is a meta, is the type of big types. So this is the universe type in this system. Okay, so a problem is solved in polynomial time if there's a realizable function that takes instances. And you have to be really careful here because this type determines what the size means, right? So this is going to contain some natural number, which you might depend on. And so you can easily trip yourself up with these complexity analyses by counting the wrong thing. So you have to be careful about what size means here. But if we can take A's to bools, and then this is a realizable function, we bring it back to just to get the extensional content. Applying that to A is true if and only if it's in the set of the language which you want to describe. Yep.
Another naive question, Bob. That R-1, R inverse, is that a term former or an operation on M?
It's a term former.
It is. Okay, so there's R and there's inverse R.
Yes. And then there's an equational rule that says when they come together, they annihilate.
Thank you.
Okay, I've got 3 minutes. Okay. To say that it's always now, right, so we can do this. So we can actually say what polynomial time is within the system. I just end up scribbling if I try and write it down, but one can also define polynomial time reductions between problems. And one can also then do further complexity classes. So non-deterministic polynomial time, we assume that we're also given a list of Booleans, which is our certificate. So then we can define that. And then we say in this correctness criterion, for all A, if there exists one that makes it true, then it's in the result. Yeah.
You only thought you had 3 minutes.
Is R defined in the language, or are you postulating some R
As,
in the meta language?
it's a new term constructor in the language.
Okay, can you still express p time in the language if we add omega? So that we then carve out p time, or does the definition here fail if you?
The definition failed. I mean, there's if you have omega, then you can express the whole simply typed lambda calculus. It can be embedded in it, and that has a complexity higher than p time.
Okay.
Yeah. So the linear fragment has to be restricted enough to capture p time.
When you say polytime reduction, are you referring to cart style or some other?
Sorry?
Can you be more specific about what type of reductions? Are they cart style?
I mean that you can go between two of these problems. There's a polynomial time function that goes from A to B such that these solutions are if and only if. Yeah, I'm not sure what.
It is cart style.
Okay. Okay, but
So if we replace set with prop,
you said it.
sorry about that. If you do the thing that I shouldn't say, could you then have reference implementation that is easy to reason about, but use a efficient polytime implementation given by the proof?
Let the poor bastard get to his punchline.
Yeah, okay, yes. I'm just going to say we can define further classes by adding in extra evidence strings to this. And then they weren't definable using the simply type system because we couldn't define what the correctness criterion was. So for NP, we say there exists a certificate that does this. We can also define, we're allowed to have a sort of a load of random coin flips. So we add effects to the system. So this becomes some distribution over bool, and we can define probabilistic classes. And I think we can define P space as well by having a free monad where you're allowed to make choices, but as long as there's an alternating choice stream through it, we can define other classes. So I think what I would like to do, and if anyone does have some money, then they can pay me to research this and to characterize other complexity classes. Maybe even do entirely Turing machine-free proofs of the Cook-Levin theorem, of NP completeness of SAT, and so on. Anyway, thank you very much. I'm sorry I ran out of time.